When working with auxiliary power systems, several crucial aspects must be carefully considered to ensure safety, reliability, and compliance with regulations. Firstly, is the auxiliary power source adequately sized to meet the demands of the intended load? This involves a detailed load calculation that considers all connected equipment and their respective power requirements. Overlooking this step can lead to underperformance or even failure of the auxiliary power system during critical times. Secondly, verify that the transfer switch is properly rated for the auxiliary load. The transfer switch is a vital component that seamlessly transitions between the main power source and the auxiliary power source. It must be capable of handling the full load current and voltage without exceeding its design limits. A mismatch between the transfer switch rating and the load requirements can result in overheating, damage, or malfunction. Thirdly, have you addressed the relaying requirements for the auxiliary power system? Relaying is essential for protecting the system against faults, overloads, and other abnormal conditions. Proper relay coordination ensures that the appropriate protective devices trip in a timely manner to isolate the fault and prevent further damage. Fourthly, assess whether the generator is sized appropriately to handle the auxiliary power required. The generator must have sufficient capacity to supply the load demand without experiencing excessive voltage drop or frequency variations. Consider factors such as starting currents, peak loads, and continuous operating requirements when determining the appropriate generator size. Fifthly, ensure that the transfer switch is rated for the inductive loads present on the auxiliary power circuit. Inductive loads, such as motors and transformers, can generate significant inrush currents during startup, which can stress the transfer switch and other components. The transfer switch must be designed to withstand these inrush currents without experiencing damage or premature failure. Sixthly, and perhaps most importantly, obtain approval from the power company for your auxiliary power design. Power companies have specific requirements and guidelines for connecting auxiliary power systems to their grid. Failure to comply with these requirements can result in rejection of the design or even disconnection of the auxiliary power system. Some power company requirements include but are not limited to the following items. Firstly, protection schemes. The protection scheme details how the auxiliary power source is isolated from the utility grid in the event of a fault or disturbance. This prevents the auxiliary power from feeding back into the grid, which could create hazardous conditions and damage equipment. Secondly, synchronization. Synchronization ensures that the auxiliary power source is properly synchronized with the utility grid before being connected. This minimizes voltage and frequency transients, which could damage equipment and disrupt service. Thirdly, grounding. Grounding provides a path for fault currents to flow back to the source, which helps to trip protective devices and prevent electrical shock hazards. The grounding system must be properly designed and installed to ensure its effectiveness. Fourthly, metering. Metering is used to measure the amount of power that is being generated or consumed by the auxiliary power system. This information is used for billing purposes and to monitor the performance of the system. Fifthly, disconnect switches. Disconnect switches are used to isolate the auxiliary power source from the utility grid for maintenance or emergency purposes. The disconnect switches must be readily accessible and clearly labeled. When planning an auxiliary power system, it is important to engage with qualified professionals, including licensed electricians and engineers who have expertise in power systems design and installation. These professionals can help to ensure that the system is designed and installed in accordance with all applicable codes and standards. Additional considerations for the system design are as follows. Firstly, performing a load analysis. A load analysis is a detailed assessment of the electrical loads that will be connected to the auxiliary power system. This analysis should include all connected equipment, their respective power requirements, and their duty cycles. The load analysis is used to determine the total power demand of the system and to select the appropriate size of the auxiliary power source. Secondly, sizing the generator. The generator must be sized appropriately to meet the load demand of the auxiliary power system. The generator should be capable of supplying the peak load demand without experiencing excessive voltage drop or frequency variations. Factors such as starting currents, peak loads, and continuous operating requirements should be considered when determining the appropriate generator size. Thirdly, selecting a transfer switch. The transfer switch is a critical component of the auxiliary power system. The transfer switch automatically or manually transfers the electrical load from the main power source to the auxiliary power source in the event of a power outage. The transfer switch must be properly rated for the load current and voltage and must be compatible with the generator. Fourthly, designing the protection system. The protection system is designed to protect the auxiliary power system from faults, overloads, and other abnormal conditions. The protection system includes protective relays, circuit breakers, and fuses. The protection system must be properly coordinated to ensure that the appropriate protective devices trip in a timely manner to isolate the fault and prevent further damage. Fifthly, complying with codes and standards. The auxiliary power system must be designed and installed in accordance with all applicable codes and standards. These codes and standards provide guidance on the design, installation, and operation of auxiliary power systems. Codes and standards such as the National Electrical Code (NEC), the National Fire Protection Association (NFPA), and the Institute of Electrical and Electronics Engineers (IEE) are some of the codes and standards that should be reviewed and followed. In summary, auxiliary power systems are complex and require careful planning and execution. By considering these factors and working with qualified professionals, one can ensure that the auxiliary power system is safe, reliable, and compliant with all applicable regulations. In more detail, let us consider the power calculation. Firstly, three-phase power calculation. The apparent power S in a three-phase system is calculated using the formula S equals √3 * volts * amps. The real power P is calculated as P equals S * power factor, where the power factor is the cosine of the angle between voltage and current. The reactive power Q is calculated as Q equals S * sin theta, where theta is the phase angle between voltage and current. Secondly, generator sizing. The generator size should be determined based on the total connected load and the expected load factor. A safety margin should be added to account for future load growth. The generator's output voltage and frequency should match the requirements of the connected equipment. Thirdly, transfer switch selection. The transfer switch should be rated for the maximum current and voltage of the connected load. The transfer switch should be designed to withstand the inrush current of motors and other inductive loads. The transfer switch should have a fast transfer time to minimize interruption of power to critical loads. Fourthly, protection coordination. Protective devices such as circuit breakers and fuses should be coordinated to ensure that the fault current is interrupted quickly and selectively. The coordination study should consider the characteristics of the generator, transfer switch, and connected loads. The protection system should be designed to protect against overloads, short circuits, and ground faults. Fifthly, grounding system. The grounding system should be designed to provide a low impedance path for fault currents to return to the source. The grounding system should comply with the requirements of the National Electrical Code (NEC). The grounding system should be tested regularly to ensure its effectiveness. Sixthly, codes and standards. The installation of the auxiliary power system should comply with all applicable codes and standards, including the NEC, NFPA 70, and IEE standards. The system should be inspected and tested by a qualified electrician to ensure compliance. Remember that power factor PF plays a significant role in power calculations. It is the ratio of real power kilowatts to apparent power kilovolts amps. A low power factor indicates a significant phase difference between voltage and current, leading to increased current flow and higher losses in the system. Improving the power factor can reduce energy costs and improve system efficiency. Then you have harmonic distortion. Harmonics are multiples of the fundamental frequency, typically 50 or 60 Hz, that can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating of equipment, voltage distortion, and interference with communication systems. It is important to mitigate harmonics to prevent these problems. Methods for harmonic mitigation include using harmonic filters, reactors, and transformers. Furthermore, transient voltage surge suppression TVSS devices are used to protect sensitive electronic equipment from voltage surges caused by lightning, switching operations, and other events. TVSS devices should be installed at the service entrance and at sensitive equipment locations. The TVSS devices should be properly sized and rated for the expected surge currents and voltages. Regarding load management techniques can be used to reduce the peak demand on the auxiliary power system. Load shedding, demand response, and energy storage are examples of load management techniques. Load management can improve the efficiency and reliability of the auxiliary power system. Consider also paralleling generators. Paralleling generators can increase the capacity and reliability of the auxiliary power system. Paralleling generators requires careful coordination of voltage, frequency, and phase angle. Paralleling generators can be complex and should be performed by qualified professionals. As an additional note, you need to review the National Electrical Code NEC requirements. The National Electrical Code NEC contains specific requirements for the installation of auxiliary power systems. Article 700 of the NEC covers emergency systems, Article 701 covers legally required standby systems, and Article 702 covers optional standby systems. The NEC requirement should be carefully reviewed and followed to ensure compliance. To further explain NEC requirements, Article 700 covers emergency systems, which are intended to supply power to critical loads, such as lighting, fire pumps, and elevators, in the event of a power outage. Emergency systems are required to be automatically activated within 10 seconds of a power outage. Emergency systems must have a reliable source of power, such as a generator or battery system. Then Article 701 covers legally required standby systems, which are intended to supply power to loads that are essential for safety or health, such as hospitals, nursing homes, and fire stations. Legally required standby systems are required to be automatically activated within 60 seconds of a power outage. Legally required standby systems must have a reliable source of power, such as a generator or battery system. Article 702 covers optional standby systems, which are intended to supply power to loads that are not essential for safety or health, such as convenience outlets and appliances. Optional standby systems are not required to be automatically activated and may be manually switched. Optional standby systems may be powered by a generator, battery system, or other source of power. When you perform maintenance and testing, regular maintenance and testing are essential for ensuring the reliability of the auxiliary power system. Maintenance and testing should be performed in accordance with the manufacturer's recommendations and applicable codes and standards. Maintenance and testing should include visual inspection, functional testing, and load testing. It is additionally very important to keep records. Detailed records should be kept of all maintenance testing and repairs performed on the auxiliary power system. The records should include the date, time, and description of the work performed, as well as the name of the person who performed the work. The record should be kept in a safe and accessible location. When working with auxiliary power systems, safety is paramount. Electrical hazards, such as shock and arc flash, can be deadly. Always follow safe work practices and use appropriate personal protective equipment (PPE). Lockout/tagout procedures should be followed to de-energize equipment before performing maintenance or repairs. Never work on energized equipment unless you are qualified and authorized to do so. These are just a few of the key considerations for auxiliary power systems. By carefully considering these factors and working with qualified professionals, you can ensure that your auxiliary power system is safe, reliable, and compliant with all applicable regulations. It is also important to remember that auxiliary power systems should only be installed and maintained by qualified professionals who are familiar with the applicable codes and standards. In summary, the key steps to take are: firstly, engage qualified professionals. Secondly, perform a thorough load analysis. Thirdly, size the generator appropriately. Fourthly, select a suitable transfer switch. Fifthly, design a coordinated protection system. Sixthly, comply with all applicable codes and standards. Seventhly, implement a maintenance and testing program. Eighthly, keep detailed records. Ninthly, prioritize safety. Tenthly, obtain power company approval. These are just a few of the many things to consider when working with auxiliary power systems. It is important to do your research and consult with qualified professionals to ensure that your system is safe and reliable.